I'm Jim Kakalios. I'm the head of the School of Physics and Astronomy. And on behalf of the school and the Minnesota Institute for Astrophysics, I want to welcome you all. Thank you for coming. Beautiful summer day. You people, but you turn your back on this lovely weather, come indoors to listen to a talk about physics and superheroes. You're my kind of people. Nerds. Yes, exactly. Remember, nerds run this planet. And we're not going to take it any more from the man. Anyway, we'll welcome you to a summer of astounding astrophysics. This is a new program that we're starting out where we're going to have professors in physics and in MIFA, the Minnesota Institute for Astrophysics, give talks about their research. And they will be non-technical for a general audience, not dumbed down, but just, explained simply so that everyone can understand it. And we hope that they're entertaining, and if not, educational. So next week, so we have this for 6 weeks, starting today. Next week, Professor Lucy Fortson, who is one of the founders, co-founders of the Zooniverse project, will talk about citizen science and how they're using millions of people to solve problems that AI can't. And I'll mention more about Professor Fortson at the end of my talk. After Lucy's talk, Professor Michael Coughlin, who works on the Laser Interferometer Gravitational Wave Observatory, LIGO, will talk about colliding black holes and gravitational waves. So it's summer, so we're going to catch some gravitational waves. Since it's summer, following that, Professor Lindsay Glessner, who studies particle ejections from the sun. We'll talk about solar flares, what makes the sun tick, and all of the amazing auroras that we've been having lately. Professor Patrick Kelly will look at gravitational lensing and talk to us about dark matter. A large proportion of the universe that we know is there and we can't see. But using general relativity, which I'll talk about today, we can. And then we'll end with the director of the Minnesota Institute for Astrophysics, Professor Claudia Scalata, who will talk about using the James Webb Space Telescope, and she has some beautiful images, and the searches for the very first forming galaxies to try to understand how everything began. So, before that, unfortunately, you have me. And I will talk to you about Superman meets Newton and Einstein. And it's kind of a nice little, primer for all the materials. Now, we'd love you to all come to every talk. You don't have to. They're each self-contained. So if you have to miss one, we'll miss you, but we understand. But you're welcome. Everyone is welcome. They're free and open to the public. So, a little background about how did a mild-mannered physics professor become associated with Spider-Man and Superman. In my day job, I'm a condensed matter experimentalist. Condensed matter is a fancy way of saying solid-state physics. Experimentalist means I work in a lab as opposed to doing theory or computers. My research actually goes from the nano to the neuro. So we make nanocrystals of one type of semiconductor, embed them into other types of semiconductors to make new materials for solar cells or thin film transistors. And then I also have projects where I collaborate with professors in neuroscience where we use techniques we developed to study electronic noise in disordered semiconductors and apply them to voltage fluctuations in the brain. But that's not why I'm here. And by the way, you could look at my background and say, hey, he's not in astrophysics. And it is true. I do not know as much astrophysics as the rest of the speakers in this series. But I guarantee you, I know more about Superman than anyone else on the faculty. So here he is. And that's because back in 2001, I created a class, a freshman seminar here at the University of Minnesota that was called originally Everything I Know About Science I Learned from Reading Comic Books, which my colleagues say explains a great deal. Now, this is a real physics class that covered everything from Isaac Newton to the transistor, but there's not an inclined plane or pulley in sight. Rather, all the examples come from superhero comic books, and as much as possible, those cases where the superheroes get their science right. I show here a cover from an issue of Action Comics that I actually bought back in the 60s. I wasn't really even that collecting Superman, but here Superman was visiting a college campus, and as a kid, I was very interested in what life in college was going to be like. And I knew this part wasn't accurate, but there are some things that were in the story that turned out to be correct. Namely, all professors at all times always wear caps and gowns, and all professors are 800-year-old white men. So I taught this class, first created in 2001, went very well. And then in the spring of 2002, the first Spider-Man movie was about to open, the one with Tobey Maguire, directed by Sam Raimi. And I thought this might be a good opportunity to get some science into the newspaper. So I wrote an op-ed on how the death of Spider-Man's girlfriend, Gwen Stacy, in 1973, in, as you all know, Amazing Spider-Man number 121, is a textbook illustration of forces and momentum. And I sent this in, and it was published in the Minneapolis Star-Tribune. The University of Minnesota put out a little press release about me saying, well, Spider-Man's on the big screen, but if you want to know about the science of superheroes, the person asked is Professor Jim Kakalios, teaches this freshman seminar, blah, blah, blah. The university has put out press releases about me before, about my work on disordered semiconductors and electronic noise. Result? Zero. You write one story about Spider-Man, however. All right, so the article came out on Friday. The press release went out on Friday. Spider-Man opened in the movie theaters on Friday. By Monday, there were calls from the BBC, CNN, the London Times. The Associated Press came to my office here in Tate, where I just happened to have these lecture demonstration tools on hand. That was a lucky break. And then this article went around the country. This is a clipping from the Chicago Sun-Times that my sister-in-law, who's living in Chicago, sent me. And then it went around the world. Here's an article that one of the graduate students brought back from Turkey, where I think I know what they're saying about me. And then I started appearing in places that physics professors don't usually show up. So this summer, if you're having a family game night and relaxing, say you're playing Trivial Pursuit, and you have volume 6, I'll tell you right now that if you get card 291, the science question, the answer is kryptons. The question is, what planet's gravity did science professor Jim Kakalios estimate by calculating the force needed to leap over an Earth building in a single bound? Now, I didn't even know about this. This just happened because I had got a lot of this press attention. So a graduate student showed me this card, and I borrowed it. I went down to the main office, and I went to my department chair, at the time, Alan Goldman. I showed him the card, and I said, Alan, who's the most famous scientist you know? And he looks at the card, and he goes, Stephen Hawking. Who's not a genius. Oh, well, then it's you. But comic books actually will get their science right more than you might think. Here's a couple of panels from an old World's Finest comic book featuring team-ups of Batman and Robin and Superman. And here, Victor Danny, a crook who has become super intelligent through a mechanism I'll tell you about in a moment, wants to find out where the Batcave is. And his henchmen protest that nobody's ever found the Batcave. And Victor Danny says, nobody with my mental power ever tried. Listen, I want you to bury sticks of dynamite in deep rock outside Gotham City and then set them off. You mean the shockwaves from the explosions can show where the Batcave is? Yes, wherever there's a cave, the wave travels at different speeds. And it'll show up like a big cave like the Batcave on my radar seismograph. This is correct. Sound waves, pressure waves do travel at different velocities depending on the density of the material. And in fact, geologists exploit this fact when they search for underground pockets of natural gas or petroleum. So here is some correct science in a comic book. Earlier, they get how science is done a little bit wrong. Here's earlier in the story, and another scientist is making a presentation at a conference to a bunch of 800-year-old white men. And he says he's developed a brain amplifier that could increase any man's mental power 100 times. But there's one ingredient that's still missing, and I haven't found out yet what it is. And I can empathize. I've invented a device that will turn tap water into gasoline and lead into gold. But it's missing one key ingredient. And as soon as I figure out what it is, I'm off to the races. And then we see here Victor Danning in the back, and he's thinking, if I had that invention and could find the missing ingredient, it could make me super intelligent. Then I'd be able to loot the world. And now this is my message to the younger members of the audience. This is what you need to succeed in life. Confidence. Just because someone else hasn't solved the problem doesn't mean you won't be able to. But also, there's a cautionary note. We see up here, one uninvited guest is present, Victor Danning, crooked ex-scientist. Because it doesn't matter how many advanced degrees you have. Once you're crooked, you're out of the club. They rip the epaulets off the lab coat and throw you off into the street. So, this may sound like a silly premise, but there's actually something serious that I'm trying to do by using superheroes to explicate, to illustrate physics principles. It will, I am sure, come as a surprise to you here all this evening. But some of my students find physics dull. I know. I feel the same way. This was driven home to me. I was coming back from lunch into this building, and I saw two students leaving. It was clearly they had just had an exam return to them. And I'm going to repeat exactly what I heard the taller student say to his friend. But in interest of the younger members of the audience, I'll clean it up. Yeah. The taller student said to his friend, I'm going to bleep and buy low and bleep and sell high. I don't need to know about no bleeping balls thrown off no bleeping cliffs. Now, there's at least 3 nuggets of wisdom contained in these 2 lines. The first, of course, where we go, the secret to financial success. So if you get nothing else out of tonight's talk, at least now you know. This is what I've been doing wrong. Buying low and selling high. The other one, for those of you who are scholars of English grammar, will have noticed that bleeping is both an adjective and an adverb. Though some of you, I think, knew that already. And the third is that many students don't find their introductory physics classes relevant. Illustrated by the standard student's lament, when am I ever going to use this in my real life? Interestingly enough, whenever I use superheroes to illustrate physics principles, students never wonder when they're going to use this in their real life. Apparently, they all have plans after graduation that involve spandex and patrolling the city. And knowing as I do how many crooked ex-scientists there are out there, that's probably a good thing. But the superheroes are just there to illustrate the physics principles. Once the physics principles are made plain, we can then show how they apply to real life everything from how airbags save lives to how cell phones work. So, in this evening's talk, I hope you're so busy enjoying the superhero ice cream sundae that you don't notice that I'm sneakily getting you to eat your spinach at the same time. So, I have to actually have a warning. Superheroes themselves are not actually physically possible. Spoiler alert. And I don't see my job as just going around saying, well, this could never happen, and this is impossible, and what's the deal with the Hulk's pants anyway? Unstable molecules. And so I grant, rather than just go around and be Dr. No or Professor Grump, I grant each character a one-time miracle exemption from the laws of nature to account for their powers. And say, well, if you were super strong, or could stretch like a rubber band, or could run at super speed like the Flash, could you run across the ocean or up the side of a building? Drag people behind you in your wake? Yes, that's exactly right, you could, right? Once you make that suspension of disbelief, you give them that one, you give them that one mulligan. Really, it's no different than, say, ignoring friction or air drag as we do in these simple problems, or assuming students care about physics. So here's a few examples to illustrate this. Here's the Flash, a DC comic superhero who has the ability to run at super speed. And a crook is shooting at him, but the Flash is faster than a speeding bullet, so that's not a problem. But there are innocent bystanders in the way. And he's not super strong, he's not invulnerable, he's just very fast. But we see here, the Flash with a sweeping motion plucked the bullets out of the air before they could harm him. And here's an explanation. Editor's note. Flash's action in stopping the bullets is similar to that of a baseball fielder who stops a hot grounder by letting his glove travel momentarily in the same direction as the ball. This is a correct way, if you had super speed, which you don't, but if you did, you could stop a bullet, because if you're running at the same speed as the bullet and you are stationary relative to each other, and you could just pluck it out of the air. Last week, I picked up something going 500 miles per hour when I poured myself some ginger ale on the airplane. It's going 500 miles per hour, I'm going 500 miles per hour, not a problem. If I'm standing still and it's going 500 miles per hour, then I have a problem. Okay? Here's actually some more advanced stuff that we will get to with Einstein later on. The Flash here in this story is trying to run at the speed of light, but he's finding it somewhat difficult. He's thinking, it's taking me a little longer than usual to reach light velocity. I wonder if I'm tired or something that could affect my super speed. Good gosh, there's no doubt of it. I'm slowing down. I'm going slower and slower despite all my efforts. I can't go any faster because I'm getting heavier. Something's happening to me. Now, those who already know Einstein's special theory of relativity know why the Flash is getting heavier as he runs near the speed of light. An alien is shooting him with a gravity increasing ray. But if you take it out of context, it's a beautiful illustration of Einstein's principle. One more example, just because I just love this because it's so goofy. For reasons, comic book reasons, the Flash can't touch anyone without killing them. And he wants to catch a bank robber, but he doesn't want to kill him, just wants to hand him over to the police. So he does some creative problem solving. He runs a half mile away and he starts racing around a pear tree. And he's thinking, by setting up a current of air, I've shaken those pears off their branches. Second panel, now by racing swiftly back to the car, I'll start a suction to draw the pears after me. And then I'll duck down and the pears traveling at high speed will do my job for me. Thereby illustrating Newton's third law of motion, which is usually expressed as for every action, there's an equal and opposite reaction. Or another way to say it is that forces come in pairs. I heard the booze. Let me just remind you that I am a teacher. Therefore, your hatred only makes me stronger. Okay, so now let's get to the main point of this evening and getting towards some astrophysics. Let's look at Superman and Newton's laws of motion, and in particular, address the question of why Krypton exploded. So, our story begins in 1938. Two teenagers in Glenville, Ohio, a suburb outside of Cleveland, trying to make some money during the Depression, create an original comic strip. Rather than Buck Rogers or people going to other planets and having amazing adventures, here someone from another planet comes to Earth and has amazing adventures, Superman. This character was so original and so unique that it was rejected by every newspaper strip for 4 years. And in desperation, they sold it to a new startup national periodicals that was looking for a feature for their first issue of Action Comics, and history was made. So, in the origin of Superman that appeared a little bit later in the comics, written by Siegel and illustrated by Joe Shuster, I'm sure you are familiar with the story. Doomed planet Krypton, scientist son Jor-El puts his only son in a rocket ship and sends him off before the planet explodes. As a father, I can empathize. Many's the time I've wanted to put my own kids in a rocket ship and send them up into outer space. And they say, I don't think the planet's going to blow up. I think it's just a truck going up the street. But better safe than sorry, I say. But then the ship lands safely on Earth, discovered by the elderly Kents, John and Martha. They eventually adopt the child and give him the name Clark. And as he gets older, he comes into a set of amazing powers and abilities, not the powers and abilities we associate with him today, necessarily. For example, in the early days of Superman comics, he could not fly, but he could leap great distances, leap 1/8 of a mile. He couldn't lift a planet, or a continent, but he could lift a car overhead. Nothing less than a bursting shell could penetrate his skin. And then when his parents passed away, he donned this very unobtrusive set of clothing and fought the never-ending battle. So, it is a well-posed physics question. How much force does it take to leap a tall building in a single bound? Okay. So, the first thing we need to know is the faster you're going, when you lift up off the ground, the higher you'll go. So here I have a little projectile that will stand in for Superman. And if I give it just one click, and the spring now is only compressed a small amount, go up a certain height. But if I give it 2 clicks, and so the spring is compressed more, it will exert a larger force when I release it. That larger force will translate to a higher velocity, and the higher velocity will go to a greater height until gravity slows it down and brings it to rest. At the height, the velocity is 0, because if it wasn't 0, it wouldn't be the highest point. It'd keep going. So, we could actually use Newton's 3 laws of motion, that an object in uniform motion will remain in uniform motion if no external forces act on it. Uniform motion just means going in a straight line at a constant speed. No twists, no turns, just straight. If there is a change, any change in motion is called an acceleration. Speeding up is an acceleration, but slowing down could be an acceleration, negative acceleration. Or if just going at the same speed, but going around a curve, that's an acceleration because you're changing your direction. And when you're in a car and you're taking a tight curve, you feel that extra force that's throwing you against the door, right? And then for every action, there's an equal or forces come in pairs, which we now know. So, Distance, we'll take a simple equation. Distance is average speed times time. If you drive at an average speed of 60 miles per hour and you drive for an hour, you've gone 60 miles, right? Now, what's the average speed? He starts off with a high velocity, but he ends with 0. So if I have 2 students in the class, one has 100, one has a 0, the average grade is 50. So it'll just be the initial velocity plus 0, the final velocity, divided by 2. The acceleration is constant. The deceleration, because gravity pulling you down, and the longer the time, the greater the speed, the longer the time it has to slow you down. And you can write this as the velocity over the acceleration g. And you get an equation that the height you'll rise, the distance, is the velocity over 2 times the velocity over g, or v squared over 2g. Or another way of writing it is v squared is 2 times g times h. So if h is 1/8 of a mile, which would certainly be a tall building in 1938, g is the acceleration due to gravity, which is constant on the surface of the Earth, 32 feet per second per second. You go on Wikipedia and you look up the value of 2. And you find that in order to rise 1/8 of a mile, he has to be going 200 feet per second when he lifts up off the ground, or about 140 miles per hour. Now, how does he achieve this enormous liftoff velocity? He does it by a process that physicists call jumping. We see here, Superman crouches and tenses his muscles for a gigantic effort. Steely muscles propel Superman up into the stratosphere. But now we know how fast he has to be going when he lifts up off the ground to rise 1/8 of a mile. So we know that that's going to be the change in velocity. He's stationary, and then when his feet leave the ground, he has to be going 140 miles per hour. Let's say that he spends a quarter of a second pressing against the ground. That's probably an overestimate, but still. We'll use Newton's second law, force equals mass times acceleration. Acceleration is the change in velocity over the time. The change in velocity is this. The time is a quarter of a second. The mass, let's say he's 100 kilograms, which would be 220 pounds on Earth. That seems reasonable. Yeah. So that means that the force his legs have to provide is about 6,000 pounds, which is why we don't see this too often. And I'm lucky to jump a trash can in a single bound. Now, it turns out there's a scientific explanation for Superman's amazing strength. Scientific explanation for Superman's amazing strength. In the comics originally, it was said that Superman came from a planet with a larger gravity than Earth. So just as our muscles and skeleton structure are adapted to Earth's gravity, so that when we go to the moon, which has a gravity only 1/6 as large, we can lift moon cars overhead and leap moon buildings in a single bound, which astonished the moon people. Perhaps I've said too much. My favorite conspiracy is not that we never went to the moon, it's that we never stopped going. Anyway, so if that's the case, then let's say we know his force when he's jumping is 6,000 pounds. Let's assume that on Krypton, he's that strong because the gravity is larger on Krypton. Let's assume that that force is twice the force his legs have to supply just standing on Krypton. And that's actually very generous. Olympic athletes typically can't exert a force more than like 20, 40% their body weight when they're doing high jumps or things like that. Well, that means that on Krypton, he would weigh 3,000 pounds. But I said on Earth, he weighs 220 pounds, which means that the ratio of the acceleration of gravity on Krypton to that of Earth is 15. So we've gone from just looking at Superman leaping a tall building a single bound to figuring out what the gravity of Krypton must have been to enable you to leap that high. But we're not done. I want to know, how do I make a planet with that much gravity? And it turns out that here we have Isaac Newton to the rescue. Now we have Professor Emeritus Alan Shapiro, who is a world expert on the history of Isaac Newton, with us. And I hope you just will not give me too hard a time for whatever else I have to say. But I'm very honored to have Professor Shapiro here. So Newton, during the Black Plague, they shut down Cambridge University. He went to his family's farm in Lincolnshire, in the countryside. There was no TV, no cable. So he basically invented physics. He came up with those 3 laws of motion. He came up with the law of gravitational attraction between objects, that it is proportion, there's a constant times the mass of one object times the mass of the other object, divided by the square of the separation between them. If we're on Earth, that means that the F equals ma. The a, in this case, is called the acceleration due to gravity. And that's the same. The acceleration due to gravity doesn't depend on your mass. It just depends on this constant, the mass of the Earth, and the radius of the Earth squared. So, oh, and by the way, to do all this, the mathematics at the time wasn't sufficient, so we invented calculus. When you look at the history of everything that Newton accomplished in a brief time while he sat out a pandemic, it's so annoying. It's just, you know, and when I just organized my comic book collection. So, anyway, so we now know, though, how to get what determines the acceleration due to gravity. So going back to the ratio of Krypton's gravity to Earth's gravity, let's, instead of writing the mass of the planet, we'll write the density times the volume. And the planets are spheres, so it's the volume of a sphere, 4 pi over 3 times the radius cubed. And that's convenient because the radius cubed and radius squared, this squares cancels this cubed. And the ratio of these two accelerations is the density of Krypton times the radius of Krypton over the density of Earth times the radius of Earth. So that means that to get this ratio 15, that means that maybe the density of Krypton is 15 times that of Earth. Earth's average density is 5 grams per cubic centimeter. Water is 1 gram per cubic centimeter. Lead is 11 grams per cubic centimeter. 5 times 15 is 75. Nothing has, no normal matter has a density of 75 grams per cubic centimeter. Uranium is 19. So you can't make it, you can't just say it's denser. Maybe I'll make it bigger. Well, there are certainly bigger planets than Earth, right? They're very special. We give them a special name, gas giants. Because if you want to make a big planet, you need a lot of atoms. You go to the stock room, and 95% of the universe by mass is either hydrogen or helium, which is why the really big planets, Saturn, Jupiter, are gas giants, which is not conducive to having cities and scientists and rocket ships and stuff. So it can't be 15 times denser, can't be 15 times bigger. Are we to assume that the story of Superman sent from the doomed planet Krypton coming to Earth with powers and abilities far beyond that of mortal men is totally bogus? No. No. I said no normal matter, but there is exotic matter. Say we had a planet the size of Earth, and this clicker doesn't seem to be working nice. And we had a planet that's just like Earth, but instead of the regular core, we put some neutron star matter in the core. That has a density of 100 trillion grams per cubic centimeter. Therefore, you only need something with a radius of 6 football fields in the center of the Earth, and the acceleration due to gravity on the surface would be 15. And thus we see why Krypton exploded. Because such an intense gravity well at the center of the planet would make an unstable distribution of mass tenuous at best. And at some point, plate tectonics would set off earthquakes and aftershocks that would alert an astute scientist that now's a good time to put your kid in a rocket ship and send him off to some other planet, preferably one without a neutron star core. So, physics can account for both the early comic book superheroes and why Krypton exploded. And this is one of the most important messages that I have to you here tonight. They couldn't put it in a comic book if it wasn't true. Now, this is comic book Superman, but of course we want to also consider the real Superman. And by the real Superman, I mean, of course, Christopher Reeve and the Superman movies. How many people have seen the first Superman movie with Christopher Reeve? Oh, I like these young people who saw it too. How many people have not seen it? Okay, prepare to have the ending spoiled. It's a 50-year-old movie. You had time. It's not hard to find. It's on YouTube. So, well, there's that. Okay, you get a pass. I'm not going to spoil all of it. But at the end, Lex Luthor set off a nuclear missile in the San Andreas Fault in California to create widespread havoc and devastation because of real estate prices or something like that. Okay, whatever. Superman, for other reasons in the story that I will not spoil, is delayed getting to California to seal up the fault. There's all sorts of devastation and destruction. And during this, Lois Lane's car, which is stalled, falls into a giant crack in the earth that opens up because of these earthquakes, and she does not make it. And Superman is heartbroken. He's devastated when he reaches her, and we see what he does here. Now, I got this off of YouTube, so hopefully it will not play the commercial. Yes, good. Okay. Oh, all right. It's not. The sound, for some reason, the sound isn't playing. But here, what he's hearing in his head is the conflicting advice from his birth father, Jor-El, who says that it is forbidden for you to interfere in the affairs of men, and his adopted father, Jonathan Kent, who says that I know that you were put here for a reason. And he remembers a time where his adopted father had a heart attack, and he said to his mother, all these powers, and I couldn't even save him. And so we see him here flying rapidly around the Earth. We're going to find out how rapidly in a second. That's a pity. No, I don't want that. Okay. Time is going backwards. Okay, we're going to get to the end of that scene at the end of the talk. But first, we have to do a little physics. How fast is Superman flying? Well, we know that speed is just distance over time. So we have to figure out the distance. How far, what is the length of one of those orbits? We have all the information we need. Okay? We know that the orbit's going out like a distance h from the center of the Earth. We know that also coming out from the center of the Earth is the radius of the Earth. And I took a screenshot of this, and I got a ruler out, and I measured h, and I measured r, and I found that the ratio was, where is it? Come on. Yeah, 1.6. And then I made it bigger, twice as big, to be more accurate, and h was twice as big, and r was twice as big, so the ratio was still 1.6. So I made it bigger still, so that the radius of the Earth was the actual radius of the Earth, and the h was the actual h, and it was still 1.6. So, knowing that it's 1.6, knowing the radius of the Earth is 4,000 miles, we know that h, the height above the center of the Earth, is 6,400 miles. Okay? So, flying around, come on, there we go. The circumference so he's going around in a circular orbit. The circumference, the distance of one orbit is 2 pi times h. But I now know what h is. And so 2 pi is 6.484. And that's exactly it. It just ends right there. So that means that one orbit is about 40,000 miles. Now, to determine the speed, I need the time. Now, he's going so fast that really what I did is I timed 10 of them and then divided by, and that would turn out to be 1.5 seconds. And so the time for one orbit was about 0.15 seconds. I know the distance is 40,200 miles divided by 0.15 seconds. So he's going 270,000 miles per second. And if you think that's fast, you're not kidding. Because the speed of light is only 186,000 miles per second. Now, Superman is always doing this in the comic books. This was his first big movie, 1978. But in the comic books, he's always flying faster than the speed of light and using it to break the time barrier and go forwards or backwards in time. And he did this so much that back in the 1950s, finally, some physics students noticed, and some students from MIT wrote to the editor of Superman comics, and they said, Superman is shown flying faster than the speed of light. Einstein's theory of relativity states that nothing can travel faster than light. How do you explain this? And this is a true story. The editor, Mort Weisinger, the editor of Superman comics, replied, Einstein is only a theory. Superman is fact. That was told to me by Mort's son. But I trust it. Whether it happened or not, it's true. So, to actually explain how going around the Earth very fast can lead to going backwards in time, we need Einstein. We had Newton, we had classical gravity, now we're going to have a more modern theory of gravity. We're going to talk about the general theory of relativity, and we're going to have Superman become a Tipler cylinder. A what now? So by the end, you'll see what I'm talking about. Okay, so let's go back to something going in uniform motion. That was Einstein's special theory of relativity, that if you're in a car and you're going at a velocity v, you can't tell whether you're moving and everything else is stationary, or you're stationary and everything else is moving. All you know is that there's some relative motion. If the speed of light is the one thing that you can't go faster than, and if everyone agrees that the speed of light, regardless of how fast they're going, has the same value, 186,000 miles per second, if they all agree that it's the same value, even if they're moving relative to each other, then they have to disagree on things like distance and time, because that's the thing that enters into speed, is distance and time. So if you're always going to agree on the speed of light, you will disagree on distances and time. So that was special relativity. And then he looked at the situation where you might have acceleration. Now, if you're in a car that's stationary, you don't know whether you're moving or, you could be moving or you could be still. There's nothing you could do inside that car to determine if there's no windows. And even if there are windows, maybe it's some Mission Impossible type thing where they're making everything go backwards and you think you're going forwards, but you're staying still. Okay? Now, if the car were accelerating, then you'd know. You'd feel an extra force due to that acceleration, F equals ma. Okay? But you could not tell for sure whether you were accelerating or you were stationary and just tilted in a gravitational field. The experiment would give you the same result. Maybe, wait, going the wrong way. Or maybe you're decelerating. Again, you feel a force. You know that you're moving. Or maybe you're just tilted in the other direction. And so this is the heart, this is all the general relativity that you need to know, is the influence of gravity is indistinguishable from the effects of an accelerated reference frame. That if you're being accelerated, and remember, acceleration also can mean just going around in a curve. Okay? So then, what did Einstein say? He wrote down, he figured out an equation that accounted for gravity that doesn't ever use the word gravity. It says, this equation, which looks rather complicated, and it is, but basically it says the mass and energy of stuff is on one side, and the curvature of space-time is on the other. And if you have mass and energy and it's curving space-time, then if you're moving through a space-time that's curvy, you're going to be accelerated. But that acceleration is indistinguishable from what Newton would call gravity, because the two are the same. Another way to put it is that mass tells space-time how to curve, and space-time tells matter how to move. So assume that there's absolutely no mass and energy anywhere. Then there'd be no curvature. So then we'd have a uniform flat space-time. Things go in a straight line. They always continue in a straight line. So here, let me see if I can get this to work. And yes, good. So here I have space-time, right? And you can see it's nice and smooth, and it's a flat. So I can send something here, and it just goes in a straight line. Now, I could put some mass. If I say I had a planet, and I put that on space-time, the mass energy on one side of the equation creates a curvature in space-time on the other side. So now, when I move by it, it slows down because of the friction on the fabric. But if there was no friction, it would just be going around in an elliptical orbit, the same thing that Newton would predict. Okay? Thank you. Thank you. I hate when I lose my mood. right? So another way of thinking, so here again, we have, yeah. So here you have a gravity well due to some planet or the sun, and another object going by it is deflected. And if you didn't know that this was a curved space-time, you'd say, oh, that's deflected because of the force of gravitational attraction between the two. And Newton would tell you how much that attraction is, and that force equals ma would cause the deflection. Einstein says, no, don't need that. Just need to know the mass of the object in the center and how it curves space-time, and that would account for the motion of the planet the same way. Okay? This is why gravity can bend light. Because say I have an accelerating car, a light pulse comes through, and then by the time it reaches the other end of the car, it is accelerated up a distance, and it strikes not this height, but it strikes at a lower point. But if the effects of acceleration are the same as the effects of gravity, then that means that if it was just in a gravitational field, it would be deflected down the same way. Because light has to travel through space-time like everything else. And if the space-time is curved, it has to take that curved path. It tries to go straight, but the surface it's on is curved. So it has to accommodate. Gravity also can affect time because clocks run slower the closer they are to a gravitational mass. This is true that your feet are younger than your head because your feet are closer to the center of the earth. And so the clock ticks slower than it does for your head. Now, you cannot detect this even with atomic clocks, but they are working on developing nuclear clocks that are 10,000 times more precise than atomic clocks. And to give you a sense of that sensitivity, they would be able to detect the time differential across your body. And the point of this would be to be able to make tabletop gravitational wave detectors. So now, why does time go slower? Well, the distance of light will travel is stretched out due to the effect of the mass, and it's more stretched the closer you are to the mass. And so, but if light is to travel the same speed, distance over time, since the distance gets longer, the time has to go slower. And the key thing is GPS, which presumably many of you used in order to avoid the road construction going on around Tate. I think their ultimate goal is to get it so that there's only one way to get into the building. There's like this one little door in the sub-basement. It's like a Batman trap. GPS wouldn't work if we didn't take this into account. These satellites, you have all these satellites on Earth, and at least 3 of them send a signal to your GPS, and it knows when it sent the signal, and it checks when the signal was detected, and you do it from 3 different directions, and you look at the time difference, and it figures out where you are relative to some point in space. And believe it or not, it works. But it only works because they take into account gravity, take into account relativity, right? These satellites are traveling relatively fast. And so due to the fact that the faster you're going, there's a time dilation, the slower you're going in special relativity, the clocks would run slower by 7 microseconds per day. But these satellites are also high up. So that means that they're further away from the surface of the Earth. Gravity is weaker. And that means that the clocks run faster by 45 microseconds. And so if there's a net adjustment you have to make due to relativity of 38 microseconds per day. May not sound like much, but when you compare it to the speed of light, if you didn't make that correction, then every day your GPS would be off by 11 kilometers, even if you synchronized it at the start. So it would be useless without taking into account special and general relativity. So you have a mass of the sun creates a disturbance in space-time. Neutron stars are denser, black holes denser still. Right? There's a black hole, Sagittarius A star, at the center of our Milky Way galaxy. It is enormous. It is, what is it? It's like 4 million of our suns. It has an event horizon that's 7 million miles far from the black hole. So don't go by it. Tempting as it may be. There's also, due to this, there's this gravitational lensing because light is bent on the curved space-time. Patrick Kelly, Professor Patrick Kelly will tell you about that in a few weeks. What does this have to do with Superman? Well, I said that I give each character a one-time miracle exemption from the laws of nature. I'm nearly done. The one character I didn't do that for was Superman, because I thought, oh, there's no way there's like one miracle exemption that could account for all his powers. Well, my book, The Physics of Superheroes, came out in 2005, and Professor Ben Tippett came up with a unified theory of Superman's powers in 2009. You should look this up. It's a great little article. And what he says is that many of Superman's powers can be accounted for if he can control the inertia of his and any matter from which he is in contact. Okay? We can all lift a car overhead if when you touch it, it suddenly has the mass of a pillow. We'd all be bulletproof if the bullets had the mass of a speck of dust. Okay? Now, we see Superman flying in outer space and there's no mass there, and I need to make an adjustment in order to account for going backwards in time. So I'm going to have, hopefully, what Professor Tippett would count as a friendly amendment, that he's adjusting the inertia of any matter with which he is near. Now, this is general relativity coming in back to us. If he's controlling the mass distribution near him, he's controlling the curvature of space-time near him. So that's how he's flying very fast. He's creating like these funnels for himself in space-time that he's going around faster and faster. One last thing I have to add. This is something that Einstein gets right and Newton would say does not exist. Imagine you're going past an object that's rotating. If it's massive enough and rotating fast enough, it's not just bending space-time, it's dragging it along with it. Like if you had a bowling ball on a bed, it would create an indentation. And now if the bowling ball were rotating, it would grab the sheet and make the sheet on the bed swirl around. This phenomena is called frame dragging, and it's real. We sent up a satellite's gravity probe B with super sensitive gyroscopes, and they were able to detect this variation, rotation of space-time that fit Einstein's prediction. And just a few years ago, looking at X-ray emissions of light falling into Sagittarius A star, which is not just a supermassive black hole, but a rotating supermassive black hole, they found that it was also frame dragging in a great. Now, Newton says a mass is a mass. Rotating, sitting still, it's a mass. That's all you need to know. Einstein says, no, you would actually go faster past something rotating, just the same way when you're at the airport, you go faster when you're walking on that moving walkway as opposed to just walking on the ground. So it gives you the same, so you get the same boost in essence in this way. Okay, so I said Superman becomes a Tipler cylinder. What's a Tipler cylinder? Well, you go to Frank Tipler, and in 1974, he published a paper in Physical Review D. Tipler was a physics professor at the University of Maryland, College Park. So this was like a serious guy. And he looked at general relativity, and he pointed out that if you had a massive enough object that was rotating fast enough, the frame dragging was such that you could actually have something that's called closed time-like curves. He actually says you could, in the abstract, it says you could actually act as a time machine. He put global causality violation because otherwise they wouldn't publish it. But what he said is take a mass of about, like, say, 3 black holes and stretch it out into an infinitely long cylinder, okay? Right away, so you're gonna need to, like, stock up on materials, okay? Have it rotate about its long axis, very close to the speed of light. It will induce massive frame dragging. And Tipler found that there were certain spiral trajectories around the cylinder that would take you not back to where you started, but back in time. That you could actually go backwards in time or forwards in time as you orbited. Now, has this been built? Obviously not. Wink. No, but it is a perfectly legitimate solution to the equations of general relativity. There are other perfectly legitimate solutions that Einstein himself dismissed, like black holes. He said, yeah, okay, that may be a solution to the equations, but it has no physical reality. Okay, so not every solution is real, but just because we don't see it yet doesn't mean it's not a solution. Or have we seen it yet, right? So here is an example, again, Tipler's two-way time machine, and this is explaining what I just described. This doesn't look so impressive. That's better. But you can get these closed time-like curves where the ball would come back not just to the same place in space, but at the same point in time, as soon as you threw it. And which meant that it must have been going backwards in time for part of that path, or you could have it go backwards in time, not even coming back to where you were. And I said we haven't seen it yet, but maybe we have. Spiral trajectories. When we last saw Lois, she was dead.
Hi. My mother thinks it's dead.
Sure is dead. The problem is still is I'm around and on. During me while you were all flying around, along the earthquake, I had gas stations blow up inside my car, there's telephone poles falling all over the road, I'm almost killed and topped the whole thing off.
Okay. So we see that when Lois Lane's life was on the line, Einstein's theory and Superman's fact came together to save the day. So I want to thank you all very much. Thank you for coming out. And I ask you all to keep up the never-ending battle for truth, justice, and the scientific way. And just a reminder and a little plug for next week's talk. Professor Lucy Glessner will talk about the Citizen Science Project, where this just came out yesterday from the Vera Rubin's Observatory. And they're asking people, all you need is an internet connection, and to help identify the thousands and thousands of different galaxies that are being observed. The disk galaxies, the spiral galaxies, the letter S galaxy. And one of the things that she will tell you about that is super cool is that the citizen scientists in the Zooniverse discovered a new galaxy that was not part of the menagerie. And it looks like a lumpy green blob, and it's called the green pea galaxy. But the cool thing is not that they just found a new galaxy, they found a new problem. There's something very strange about these galaxies. And I will not tell you which, you'll have to come next week. But science is not about knowing all the answers, it's about asking the right questions. And what the citizen scientists did by discovering the green pea galaxy is they found a new question. And that's what keeps us all going. Thank you all very much. I will take some questions. We have time. I went over long and I apologize. Questions? Yes, sir.
One observation, one question. The observation is, couldn't have Superman just gone around the Earth in the opposite direction, which was rotating at a particular latitude, and go back in time? That's the observation.
Okay.
The question I have is, I've seen this in textbooks all the time, where they say, you can't tell the difference between acceleration and gravity. And there's these pictures of dropping balls in an elevator. But you can. And Einstein did a lot of thought experiments. If you drop two balls and the elevator is accelerating, they can be parallel to each other. If, however, it's gravity, it is going to be, even though you might not be able to measure it, the two paths are going to be converging. So you can tell the difference. Question.
So the question is, so there was an observation about Superman's trajectory,
Yeah.
right? And I'm glad you brought that up because I nearly forgot. For everyone who's still here, I did not get into the specifics of the spiral path. So for everyone here, next week, homework. You can thank this guy. We're going to meet you with a sack of oranges outside. I have not thought about this point of what you're saying because there's a converging focal points. I have a colleague, Michelle Jansen, who is a historian of science and an expert on Einstein. He was one of the editors of the Einstein letters, and his specialty is general relativity, in fact. He has a brilliant talk, what did Einstein know and when did he know it? How he developed the general theory of relativity. I promise I will talk to Michelle about this. And if you're here next week, I will be here. I will host all of the talks. And I hope to have an answer for you.
Good, I'll be here.
Okay.
What about the first one, the observation about the...
That's the homework problem. Yes, go ahead.
Einstein, Superman, kind of went around the Earth and then, kind of going back onto the Earth.
Yes. So Superman went up and he went around the Earth, you're right. But then he went back to the Earth. That's right. Well, I mean, Superman can fly. He can't. He can do more than just jump great distances anymore. So, you know, I may not be able to understand how he does it, but as better people than I have said, Superman is fact. So this is what we have to deal with. But I agree, it's a good point. Yes, there was a question there. You have an observation. I'm sorry, say again? Could you say a little louder? Oh, yeah.
Considering that Superman doesn't have the curvature of space, does that make him an algorithm?
Does that make him what?
Algorithm.
Oh, I'm not sure what that is, but he probably is. I mean, if he's able to warp space-time at will, then presumably, I mean, which is how he's able to fly in outer space and go at such great speeds, because he's just creating out of space-time this enormous slip and slide that he's falling through. Then sure. I mean, one of the things about this is not to actually explain things from a superhero movie or a comic book, but to use them as the jumping off points to talk about some real science. And the amazing thing is, by thinking about this scene in the Superman movie, led me to Tipler cylinders, which is something that I didn't see in any of my classes. So it's by thinking about these things, how could I make this work, that leads me to some fun adventures. Yes, yeah, and then you, okay? Go ahead. Could you speak up, please?
Is that no matter what you can do, the gravity happens. Let's not get hypothermia.
So the question is, how does Superman avoid hypothermia? How does he, well, super breath. He actually, Tippett explained super breath as part of this miracle exemption. So I don't recall offhand. He also explains heat vision as part of this. No, he's got heat. Laser eyes, please. Let's keep this on a serious level. But yes, definitely. Tippett, you should look at Unified Theory of Superman. It's a fun article. But again, it's taking something that's not real, and basically. But yeah, I agree that with the arguments, arguing it is perfect, because the thing is, we're saying, what is the minimum law of physics I would have to change for this character's powers to work, or for this character to be doing what they're doing? And that's what we do in scientific research. Enrico Fermi said that when your observation agrees with your expectation, you've made a measurement. When your observation disagrees with your expectation, you've made a discovery. Because you go into the lab and you expect the experiment to give you result A, and it gives you result 62. And so then the thing is, well, all of space-time is wrong. Or maybe the charge of the electron is not what I thought it was. So you try to take the minimum amount that you could change, and from that, our understanding of the universe increases. Yes?
So given that this does imply time travel and causality breaches, do you think, at least in your opinion, that what Superman is doing here is a causality breach or a breaking timeline?
It is definitely a causality breach. It is unquestionably. Einstein's friend Paul Erdős, who did the incompleteness theorem, for a book that put together from people writing scientific papers in honor of Einstein's 70th birthday. He wrote one that said, if the universe is rotating, if the universe itself is rotating, then it would be very easy to get closed time-like paths, and time doesn't mean anything. So if general relativity is correct, then time is meaningless. And he gave it to Einstein, and he was so proud, and Einstein said, thanks a lot. And he said, well, once again, another thing that the theory might predict, but is not, and as near as we can tell, the universe is not rotating, the universe as a whole. So people are constantly trying to develop different ideas. I mean, but it's, as thought experiments, I think it's very interesting and fruitful to try to push these theories as hard as you can and see what results come out of it. Okay, one more question. I'm going to take it way in the back. Yeah, yes, where do I find all the comics?
In our basement.
Yes, thank you, dear. My wife doesn't call them the comics. She affectionately refers to it as the fire hazard. The benefits of a misspent youth, adolescence, middle age. I remember early in our courtship days, Therese just turned to me and said, "You're not going to outgrow this, are you?" But I don't think of it as a guilty pleasure because I don't believe in guilty pleasures. You like what you like, and as long as no one else is hurt by it, then, enjoy. So, anyway, thank you all very much. Thank you for coming. I hope to see you all here next Tuesday. Citizen science.